In this lesson, we're going to focus on the HTTPS handshake, and after we've gone over the handshake, we'll be in position to configure a production-grade web server such as Tomcat to accept HTTPS connections. So let me begin with two slides that contrast two different approaches to encryption and decryption. The first approach is sometimes called Singlekey or Symmetric, and the idea is this. If you start over on the left, you see plain bits. These are unencrypted bits. So for example, the bits that make up a message sent from a client to a server or in the other direction. These plain bits are put through the encryption engine. They're one input. The second input is a numeric value, the single key, which is used to transform those bits into cipher bits. Basically, this is an arithmetic computation. The cipher bits then are the encrypted bits, and on the receiving end, they go through the decryption engine using, and this is the critical point, the same key that was used earlier to do the encryption. And of course, if all goes well, you recover the original plain bits. Now, let me contrast this with a second approach. This is called asymmetric, or more commonly key pair encryption and decryption. And the picture is a bit more complicated because now we have two separate keys. For example, a public key from a key pair and a private key from a key pair. The public key, if used for the encryption, requires then that the private key be used for decryption. It's possible, by the way, to encrypt in the other direction. In other words, to use the private key for encryption, in which case the public key would have to be used for decryption. Now let me go back to the original. The single key encryption-decryption has a tremendous advantage. It's roughly 1,000 times faster than the alternative. The problem is what people call the key distribution problem. In other words, if I'm the client side and I have the single key, how do I get that key over to the other side without having it intercepted? This is basically the key idea behind the handshake. So let me now bring up my Emacs editor, and this working file is called handshake.txt. It gives us the short version of the HTTPS handshake. So recall from the last lesson that the underlying algorithm is this, quite a mouthful, ECDHE. By the way, this is normally abbreviated simply to Diffie-Hellman, the two researchers who came up with the algorithm. Now, I'm going to focus only on the client side. If there's true peer authentication, in other words, true mutual challenge, then basically you would have challenges going both ways. Okay, step one then is this. The client, so the Google client code we saw earlier, or a browser, challenges a server. So we'll assume this is the Google web server. And the web server responds with one or more digital certificates from its key store. The client then uses its own trust store to verify these digital certificates. If the certificates are verified, we continue. If not, we're done. In the third step, the client generates what's called a pre-master secret. So typically, browsers nowadays will generate a 48-bit value. It has certain cryptographic properties. We don't care about those so much. The pre-master secret is going to be used to generate the single key on each side. Now the trick, and this is the critical step 4, the trick is to get that pre-master secret over to the other side so that it can't be intercepted. To that end, the client uses the public key from one of the digital certificates it got from the server. So you'll recall that Google actually sent 3. So the client picks one of those public keys from a digital certificate, and it encrypts the so-called pre-master secret before sending it to the server. The server will then use its private key to decrypt that secret. Now at this point, life is good. The client and the server have the same pre-master secret. They've already discussed, in effect, the algorithms that are going to use to do all of this. So they use that pre-master to generate the secret key, the single secret key, and in the web, this is typically described as the session key. So in the example that we saw, that session key is going to be 128 bits in size. This is configurable. You might have a 256 or a 512-bit session key. At this point, the session key is going to be used on both sides to encrypt and decrypt messages, and this would be significantly faster than if the two sides were to use public key encryption. By the way, at any point, if either the client or the server suspects that a bad guy has somehow come into play, either side can ask that the handshake be repeated. So, for example, either side could say, in effect, I think we need a new session key. Let's do the whole thing over again. Exchange certificates and all of the rest of it. Now, with this wrap up, we have enough information to talk about something very practical, that is, how to take a web server such as Tomcat, which comes out of the box ready to do HTTP, but not ready to do HTTPS. So we'll take this background information and we'll apply it in the next movie to configuring Tomcat.